Check it out now, y'all.
NanoHub U, online instruction.
Welcome back. You may remember that we had been discussing this third topic related to nanobiosensors having to do with selectivity, that ability to differentiate between the molecule that you are really after and the molecules which are floating around but still can come and contaminate your signal if you're not very careful. Now, we said that there are two important fundamental ways by which the signal contamination can take place. One has to do with energetics, that when two biomolecules attach to each other, like two pieces of DNA, two polymers of DNA, even if they are not perfectly matched, they can still bind. And if they get bound, the sensor underneath will appear as if a right molecule has been captured. That was the first type of selectivity issue. And the second one was that, in a sensor surface, you have the receptors in various places, but there is a lot of empty spaces where a molecule can just come and sit there. And as a result, in that case also, there may be parasitic signals. Now, as you saw last time in my discussion, that these may be fundamental. And if they are fundamental, there is nothing much we can do about it. We can increase the temperature a little bit to differentiate between target molecule and the parasitic molecule, but sometimes the gap may be just too small. What do you do in that case? And today I'll give you a recipe about what can be done and what people have been doing. And the basic point is this: when all else fails, tag, filter, and amplify. So I will start with this notion about how to improve signal, and then we will go through a way of improving signal is called polymerase chain reaction. And this is one way of improving signal, but of course you could also suppress the noise, right? If you could somehow suppress the noise, that would also give you better signal to noise ratio. We'll discuss that next before we conclude. Just to get back to the original problem, you remember that there have been some biomolecules sort of floating around, diffusing around, and they are being captured by, let's say, these four sensors in the solution. And of course, we are generally interested in the capture of the right molecule, which is, let's say, the red, with the correct sensor. And that's the red term in here that says that if the red molecules were there alone, there were no parasitic blue molecules around, then the signal would be 100%. That's the red term, because that would be the term saturated density when biomolecules simply come and attach to the sensor surface. But as we saw, that when you have these blue molecules around, this parasitic molecule around, they can also come and sit on the sensor surface, giving a parasitic signal, a spurious signal, which is not the real signal. And therefore, that was the second term. And this is something we discussed in lecture 25. The third term was molecules sitting in empty spaces. That is the black term. So we also discussed that. So somehow what we are talking about in this lecture is somehow can we increase the red? Can we increase the signal? Can we improve or increase the number of red molecules? Or can we somehow make the blue or the black term smaller? Right? These are the two things. Because if we can do that, then of course we'll be able to have a better signal to noise ratio. Now, as I just mentioned, therefore, and if we have more of these red molecules, and then therefore what will happen is that the coefficient alpha, which is the fraction of the right molecule divided by all the molecule that has been captured, the fraction of alpha will go up, and the beta, which is the false positive, that will gradually go down, because as soon as I have very large NT, the beta is inversely proportional to NT. So larger is the number of signal molecules, then lower will be the beta. Of course, the beta will also get smaller if I can somehow reduce NT and N geometry. And that will all get reflected in a Bader matrix of the sensor, so that when you have a certain molecule, let's say 1001, then it will be reflected more properly as 1001 rather than some other combination. The beta will be very small, alpha will be relatively large, and so there will be highly selective detection of the biomolecule. Now, one way, matrix is one way of viewing the sensor problem or the selectivity problem. Another way of viewing it that is very helpful is to think about the whole problem as a special example of information theory. Think about it. Let's say you have a DNA sequence 1001. 1001 meaning that you have a certain target molecule here, there's no target molecule in second and third place, and you have a target molecule on the fourth place. Now you are trying to, this is in the solution. That's the message. The message is in the solution, and you are trying to read that or capture that message. And of course, what is hindering you are all these parasitic molecules, all these homopolymers. I'll explain what it is. The sensor noise associated with it is making reading difficult. And as a result, although I had a sequence 1001, that was my combination of molecules that I had in the solution, I'm reading it somewhat slightly differently with alpha plus beta, beta, and alpha plus beta, a slightly different sequence. And the reason I'm reading a slightly different sequence, because the channel, when I was reading it, the information carrying channel essentially added this noise. So somehow, all the theories that we have from the information theory about how to reduce noise and how to enhance signal will come in handy. So how do you enhance signal? Well, one way to enhance signal is to send the same message over and over again, right? Having more repetition. And that way, even though you have signal, after averaging over many times, you will get better signal to noise ratio. The other way would be to make the channel better so that you suppress the noise. So this two-way, the matrix way of looking at the sensor problem for selectivity and the information theory way of looking at that the selectivity problem are essentially all equivalent, and essentially one can be mapped easily onto the other. So let's get started by saying how can we amplify the signal. So here we are talking about, let's say, DNA. So how do you get DNA first of all? First of all, you have a cell, and if you add a small bit of detergent, for example, immediately the cell walls will dissolve. And the cell walls will dissolve and the content will come out. But remember, this is a grab bag of lots of different types of protein, nucleotide, nucleus, cell nucleus, all sorts of different types of things are within the bag. How are you going to get the protein? Well, the way to get it is what they call is to centrifuge it. So what you have here, put it in the solution, the content of the cell in the solution, and then spin it at a very high speed. And when you spin it at a very high speed, it turns out that the slightly heavier proteins or molecules essentially get to one end, and the slightly lower masses or molecules with lower masses, they sort of stay close to the center. And then you can essentially pour out the more lower mass solution and then gradually keep filtering. So by filtering, eventually you can get to the DNA. So how does a centrifuge work? The centrifuge actually is a very interesting device because it will rotate at an acceleration of about 100,000 G. It's possible to achieve that high speed or acceleration. And the way it works is that, let's say you have two molecules, one a little bigger, one protein a little bigger, and another one is a little lighter, the white one. And so what would be the downward force? The downward force would be mg if it was in air. But because of the buoyancy, this will displace this molecule, the red blue molecule will displace the liquid volume, and V multiplied by rho essentially is the volume of the mass of the displaced fluid. And so that will give it a upward push. That's the buoyancy force. And so therefore the net mass will be m prime, and that will be then pulled down by the gravitational acceleration g. Now remember, this molecule is tiny, very, very small, and therefore multiplying with g doesn't give you much force at all. However, what you can also do is you can write down the downward force also in a slightly different form. You can say that as the molecules are gradually getting down, m star m prime vd is the net momentum going down, and they are getting scattered every tau seconds. So the net force down is given by this relationship. Now you can multiply top and bottom, q with q, in here and flip the m star. Q tau over m star is known as the mobility. If you don't know this definition, for the time being, just go with it, saying that this is by definition is the mobility. And then once you know the mobility, you can write it d over mu by Einstein's relationship is kt over q. You substitute it in here, you get a relationship between force, downward force, and the diffusion coefficient of the molecule within a given fluid. And so you can balance these two. These two must be the same thing in both cases. So if you balance the two and take a ratio of the drift velocity downward or saturation velocity downward with respect to the acceleration, then it's given by the net mass diffusion coefficient divided by kt. Now, therefore, you can see the velocity is directly proportional to the mass, and so therefore the blue will go a little further down compared to the white protein. How fast, how far more will it go depends on g, because if you cross multiply with g and the g is 100 times the gravitational constant, let's say, or 100,000 times, then even if the mass difference is very small, they can get separated relatively quickly. And so you do this centrifuge, and then the molecules essentially get separated. You do a low speed centrifuge, so therefore you have a slightly bigger molecules in the bottom and smaller molecules on the top, and you can then separate them out, and then subsequently you can separate various pieces out, and then these various pieces will be your DNA. But you have a very few copy of DNA. That's you, so you have not amplified the signal yet. So how do you amplify the signal? You see, I have just extracted the DNA, but I have not really amplified it. And this is how the amplification goes. So this is the general idea, that there is something called a polymerase chain reaction. This is a way of amplifying a signal. Just like if you have a music which is very low sound, you can use the amplifier to make the sound bigger. The same thing you can do with the DNA that you just lysed. The word lyse means to break apart. So after lysing the cell, you got DNA, and the DNA you can amplify. And the way you amplify in the first cycle, the 2 DNA in the helix will become 4 after the first cycle, and I will show you how this is done. After the second cycle, it will be 8, third cycle 16, fourth cycle 32, and the general idea is that every cycle it increases by a factor of 2. So after n number of cycles, you will have 2 to the power n. And, you know, if you have to 35th cycle, let's say, you may have 60 million copies of this. So this is somehow, you can start from just a single DNA, and then it would be very difficult to find in the background of other proteins, that single DNA. But if you amplify it, very soon, this total number will be far larger than all other proteins that you have. And in that case, you'll be easily able to detect this molecule, the DNA molecule. So how does it work? The PCR molecule, essentially it has 3 steps. First you do the denaturation, which is increase the temperature of the solution to 92 degrees, and it breaks the DNA apart. You remember, right, that if you have a certain DNA, we looked at the melting temperature, if you have ATCG, you simply calculate how many binding it has, and then we calculate the melting temperature. Let's say if you increase it to about 92 degrees, then they get broken into two pieces. Now, once you have it broken into two pieces, the next thing would be to add this primer. You see, this is one broken piece on the left and another broken piece on the right. And wherever, when you want to start copying it, you have to throw some primers in. Primers means that is where it will begin to assemble itself, reassemble itself. So you can see that there is a primer here, the primers are floating around, and the other primer is also attaching to the center, to the individual single-stranded DNA. And then what will happen is, in the solution, if you add a lot of ATCG, all these molecules will randomly come and attach to the sensor surface A to C, A to T, C to G, and gradually it will build it back. And very soon you will have two copies of the original DNA. So this is cycle 1. Then you can do this cycle again. Each one of them that you just formed will now become 2 more. And so there will be 4, 8, 16, and so on and so forth. So generally there are these 3 steps then. If you look at the concentration of the double-stranded DNA, let's call that U3. The concentration of single-stranded DNA is essentially a factor of 2 larger, because you just have divided into 2. I will call that U1. And then the primer DNA, when the primers have attached to the DNA, we'll call that concentration U3. And you can write 3 simple differential equations to describe how the numbers are evolving. So for example, we can write first, let's write one for U1, the single-stranded DNA. The first term on the right is the diffusion. So the molecules are diffusing around. They may or may not have yet met with the primers. And KAU1 is the rate at which it is meeting the primers, so they are no longer single-stranded DNA. That's why they are leaving the concentration unit. And at the same time, a certain number may, at that temperature, double-stranded DNA may break into 2 pieces, so that gives you 2. KDU3 is the rate at which single-stranded DNA are being generated. Alright, and the rate constants are KD and KA. So those are the 2 rate constants I have written in the differential equation. This diffusion coefficient is simply saying that they are swimming around. Now what about U2? U2 is the prime DNA. Remember the long DNA I had, I start at a point, given point, that's the primer. Primer sort of initiates the rebuilding process. And for U2, we'll have the same thing. The molecules primed molecules can move around, diffuse around on their own, or they can sort of be joined by some single-stranded DNA which has just captured the primers, or they can essentially go back and after completing the double-stranded DNA process, then they can essentially join this population because the building up of the DNA is now complete. So they are no longer just a simple prime DNA, but they are really the double-stranded DNA fully built. So you have then essentially these 3 differential equations. You have the unknowns U1, U2, and U3. The rate constants are all given, and therefore you can solve these equations. So I'll show you some examples about how the signals are getting amplified as a result. So for example, let's take one example where the problem has been solved. And here you see the population of single-stranded, or let's start with the double-stranded DNA, which is the red line. So in the beginning, I had 1 double-stranded red line. On the very left at time t equals 0, I had a value 1. You can see this tiny red poking up. Then as soon as you raise the temperature, the red went down. Why? Because they essentially dissolve into 2 single-stranded DNA. Now, after the first cycle is complete, then the number of red DNA is 2. Then when the temperature is increased again at 92 degrees, the red DNA concentration went down because double-stranded DNA once again dissolved. And you can see then when they were rebuilt, it was 4, 8, 16, and 32. And every time you can now sit down and follow the single-stranded DNA. The blue curve essentially starts at 0 at time t equals 0. But after the very first cycle, essentially you have 2, because from the single-stranded, double-stranded DNA, you got 2 single-stranded DNA. That is the blue curve. And essentially you can follow the curve and correspondingly see that the single and double-stranded DNAs are essentially alternating with each other as they go through this cycle. And you can see that therefore you can have significant gain. Even after 5 cycles, you have 32, a 32 number of copies now available for the double-stranded DNA. Now, a very important point of this amplification process is that you have to give enough time, because these are reactions, right? And so if you don't give enough time, so what happens that let's start on this one with the red curve. Red curve is double-stranded DNA. You started with sort of 1, but you didn't allow it enough time to sort of break apart. And so therefore, this hasn't really gone to 0. And therefore, the corresponding double-stranded single-stranded DNA in the blue curve also didn't reach their full value. And therefore, when this thing oscillates back and forth, because the reaction is never complete, right? You are not allowing enough time. In that case, you see at the end of the 5th cycle, you only have 12. So if you try to do it too fast, in that case, your amplification will not be very good. Same thing is true. So for every space, if you don't allow enough time for the annealing, right? And in that case, the same thing will happen, and you will see the amplification will not be significant. Finally, there is also another reason why the amplification may not be complete, and which is that in every solution, you need a certain amount of primer. Remember this string of molecules which sort of started the process by attaching it to the long DNA, so that subsequently the building process can start. That's the primer. And in this case, the primer concentration, if the primer concentration is finite, then what will happen that after every reaction, this primer will be consumed because they are getting incorporated in the DNA itself. And as a result, after the primer concentration runs out, let's say after a finite number of cycles, then this will completely saturate. It doesn't matter how many cycles you do, it will completely saturate, because in this case, there's no primer available, so the cycle cannot simply continue. So this is very important because for finite simple systems, for nanobiosystems, if the primer becomes a constraint, then the amplification may not be complete. So what I told you is how to amplify signals. So let's say you started with 1 copy of DNA. After 5 cycles, you can make it 32, or you can increase the initial concentration by a factor of 32. Your signal to noise ratio simply went by a factor of 32. So therefore, the probability of false positive or false negative was considerably, or false positive and negative, and both of them would be considerably better compared to before. Now let's see if there's any way to reduce the parasitic signal, and because that way will also improve the signal to noise ratio. Once again, we'll be focusing on, is there something we can do which will make the noise channel less noisy? In fact, those approaches, how to make channel less noisy or how to suppress this, has been known to people for a very long time. For example, let's say on the left-hand side, we have a DNA. The DNA looks like a hairpin, and it's called a hairpin loop. And you have this little marker molecule, it's like a star. And initially, let's say the star is dark. When the biomolecule comes and attaches to this binding, it is relatively selective. And therefore, it essentially unhooks the hairpin loop, unbinds it, and then you can look at it through these tags. Now, of course, all the other molecule which is not so selective to this DNA, hairpin lip DNA, will not bind. And therefore, by looking at these optical tags, you can only pick out those molecules that are actually target molecules. The parasitic molecules will not be able to unbind this and create make this optical tag active. So this is one way by which you can improve signal to noise ratio. But there is a very nice way, that is another very nice way that also solves this problem. So assume that you have a probe DNA, you have this green target DNA, but on the head of that target DNA, you have attached a big magnetic nanoparticle. Now, if you have a big magnetic nanoparticle, then after binding, there will be this green magnetic nanoparticle which will be sitting very close to the sensor. Now, if this sensor can detect this magnetic particle, right? It could be a spin-based sensor or some other sensor which can essentially find that there is detect the presence of a magnetic particle. See, there will be several advantages. First of all, there will not be any salt screening because magnetic interaction will not be screened by the salt. That will be good. Also remember, none other of the particles have this parasitic particles have this magnetic nanotag with it. So therefore, although they may be floating around, this sensor, this magnetic field-based sensor will not notice them. As a result, you will have significant suppression of the noise or correspondingly amplification of the signal depending on how big it is. Now, how are you going to find the target molecule and attach a magnetic tag? Do you remember the biobarcode approach? In that biobarcode, essentially, this is exactly what was done, was to attach a magnetic particle so that you can sense it with a sensor. So that's a possibility. So let me conclude then. As I said, that the selectivity problem is very important because you see, nobody wants to hear that he or she has cancer, although in principle the person may not. So in that case, if you are looking for a cancer protein, one must find the right protein and catch it and report it, not the parasitic molecules which will tell somebody that he has a cancer, although he hasn't. Actually, he doesn't. And in this case, this problem of selectivity can be viewed in two ways, I mentioned. One is that you can think about it as a matrix, and you have a vector, which is your input target molecules, and the response is another vector, which tells you whether the molecules are present or not. If the matrix is extremely diagonal, then it's very selective. The other way you can do it is by thinking about comparing it to the information theory. That's another way of thinking about this problem. Now, the signal to noise ratio is very important, and one way you can improve the signal to noise ratio for DNA, you can use this polymerase chain reaction, which essentially doubles every cycle, it doubles the count and therefore improves the signal greatly. The other way would be to resample time and again. So do the same experiment over and over again. The noise will average out, but the signal will stand apart. So that is another way how you can improve the signal to noise ratio. And finally, in order to improve the signal noise ratio, you can suppress the noise. How do you do that? Attach a magnetic nanoparticle. And the magnetic nanoparticle will essentially allow only the target molecules to induce a signal. All other proteins floating around, they don't have any magnetic nanoparticle attached to it. So therefore, their presence will not be registered by the sensor underneath, right? So these are not potentiometric sensors. These are magnetic field-based sensors. In that case, signal to noise ratio can improve a great deal. So let me stop here in terms of selectivity issues. In the next two lectures, we are going to sort of bring together everything that we have learned until this point until, let's say, lecture 27, all these 27 lectures, and show how all these pieces essentially enables a modern genome sequencing system and how powerful it is. And so until next time, take care.